to this session on understanding graphs and linked lists from an exclusive DSA. A data structure is a particular way of organizing data in a computer.
Graphs. So before that, a bit about myself. As mentioned, I'm an application engineer at Google. So before Google, about me, I have worked in TCS and Oracle. In TCS, I have worked as web developer and data engineer. And in Oracle, I have worked as a web developer, a full stack web developer. And after Oracle, now I'm working in Google. In Google, what we actually do is we work on remote collaboration and SEO. So here are my links for LinkedIn, GitHub, and YouTube. Please arrays which are just empty, right? Elements of arrays which are empty. Plus, arrays are fixed size, so we actually cannot increase them. Now, one block allocation, what it means is that we have to allocate entire memory in the beginning. Like we know that in arrays, the memory allocation is sequential. So if our systems do not have enough memory, I mean, nowadays that doesn't happen much, but if our systems do not have enough RAM, then we would not be able to create a large array. So the next thing is complex insertion. What does that mean is that whenever we want to insert any element in an array, we have noticed that we have to rearrange our entire array. Even for deletions, we have to again rearrange our entire array if we want to delete elements as well. So if not arrays, then array lists, right? Why not array lists? So the problem with array lists is same as arrays. So deletions, we have to again rearrange the entire array, because array lists, what they do is they use arrays behind the scenes. The next thing is again space allocation. When we create a new array list, what happens is it allocates certain space to it. I guess it's 8. Not sure about other languages. And what happens is if we exhaust the space of 8 elements or 16 elements, what it does is it allocates it creates a new array, and the length of the array is 16 plus half of 16, that is 16 plus 8. So the new array would be of length 24. And same thing will happen when we exhaust the space of 24. So 24, and again some new length of 12 elements. Now that is how array lists actually grow. And here we can see that there can be a lot of elements or blocks of memory which can remain unutilized for array lists. Plus, we see that for cases where we have heavy inserts and deletions, it might not be very optimized approach to use it. So, what to use then? Linked list, right? So, linked list is like, I know a guy who knows a guy. So we have nodes, and each node connects to our linked list, and we reach the last element after which the next node would be null, and we keep on increasing the counter, and the counter is actually the length of our entire linked list. Now, insertions, right? So if you notice, I'm using this annotation of list node of type T. It is very much related to Java and used a lot in Dart as well. So let me give you a background about it. It means that a list node of type T, right? So a list node can be of type string, object, string, numbers, integers, object, person, anything. So the thumb of rule is whenever we are trying to do any and we are trying to write an operation, what we should do is we should always take care of our base cases. That's the first thing we should do, and that is what we have done here. We check if the position is less than 0, or the position is greater than length, where we have to insert. If any such of the things happen, we say that we cannot insert it. And after that, it's pretty simple. So we just keep track of our nodes, of our position, and As soon as we reach our node where we have to add it, what we say is the new node's next pointer would be pointing to the difficulties when we are solving. Now, the problem here, which you may find, is that problem solving is that we often lose track of pointers, which node is pointing to which node, and if I'm keeping track of all my nodes or not, right? We'll see how we can make sure of that. Now, while doing a single linked list, I traverse the list, I reach a node, and then I have to go back, but I cannot. I have to again start from here, and that's not very good, right? So, what do we do? Doubly linked list. So doubly linked list is a bit different. The only difference is that we just keep track of the previous node and the exact data structure. The linked list data structure, what it does is it keeps track of head and tail. It's well, we can just work with head, but I like to keep track of tails as well. It just makes traversal much easier. And in certain questions, so let's say if you have to find a midpoint, right, of a doubly linked list, then it helps if you just start your pointers from start and end, and then meet them at somewhere in the middle, right? Unless it's a single linked list, linear single linked list. In that case, what you'll have to do is you'll have to do two pointers, one fast, one slow, and then calculate your middle value. So traversal for double linked list is pretty similar to that of single linked list, and we just keep track of our position and the current node. Just a second. All right. So here's a new node which we'll have to add. All right. Now what we do is we say that let's say we have to add it here. List continues, and we have to add it here. Now we traverse our link to this point, and now what we do is we have our current node, and this is the next node. There does not say this is the next one because we do not point to it at any point in time. So what we say is my node's next node should point to my current's next node, which is this, right? And my node's previous node should connect to this. This is simply what we are saying here. The next thing is, what we are saying is, the next node's previous value, this previous value should point here. So now we lose this link. And my current's next value should be this. So now we lose this one. Now, the thing to note here is this is pretty simple example, but the thing to note here is that at no point of time we have lost track of the nodes which we need. So the nodes of interest here were this current node and our node. Right, it was easier to keep track here, but let's check the other example. Before doing the node will be garbage collected by the system itself. So, or we can just mark it as null and remove its use and save a GC cycle ahead. All right. So this is how important it is to, while we are doing linked lists, always keep track of what you're trying to do. All right. As in, when solving a linked list, make sure that All right. So let's talk about circular linked lists. So circular lists are mostly similar to single linked lists, just that the tail is connected again to the head. Now, I like to keep track of tail rather than keeping track of head, because if when I keep track of tail, I can keep track of the head as well. And to be honest, tail and head is just relative terms, because in a circular linked list, they do not have any such significance because it's circular, right? So let's do some DSA. Now, like I just mentioned, as soon as you read a question, you should not start typing. You should give it some time. You should take a breather and draw it up on a whiteboard, on a notebook or somewhere. So what we want to do is we want to find uh, the beginning of a circular linked list if there is a loop. What does that mean? It means that we have a list and possibly there is some loop here. All right. Let's name these linked lists. Let's say just 1, 2, 3, 4, 5, 6, 7. All right. So and say this is head is pointing to this node. Now, a brute force solution which I can think of is I can traverse through this list, right? And as soon as I find a duplicate, I'll say that it has a loop. Now, how do I do that? I can use a hash table kind of implementation, say a hash set in Java or an unordered set in C. So I'll put 1. I'll go to 2. Is 2 present in the list? No, I'll add 2. Is 3 present in the list? No, I'll add 3. When I say list, I mean the hash table. So then I go to 4. Is 4 present in my hash? No, so I add 4. Is 5 present? No, I add 5. Is 6 present? No, I add 6. 7 present? No, I add 7. I again come to 3. Is 3 present? Oh, yes. So since 3 is present, it means that we have a loop at this point, right? However, if we talk about memory or space complexity, it's kind of O(n). And what we would like to do is do it better. So once you provide your brute force solution, the interviewer may ask you to provide you an optimized solution. Now, the optimized solution here might not be very obvious. However, in this particular case, most of us have done this question, probably. Even if not, you would certainly do it while you're practicing linked lists. And the problem here is understanding that why this particular algorithm works. Now, one thing which we can think about is if we have a fast pointer and a slow pointer, and we are moving that in a loop, then there can be a scenario when those 2 pointers meet at a point, if there is a loop, right? Let us work with that theory. And all right. So if we have this is my fast pointer and I have a slow pointer. All right, and then I have a head. All right, so my fast pointer moves faster than my slow pointer. So how much? So my fast pointer moves twice as fast as my slow pointer. Right? Now, when my slow pointer reaches this point, my fast pointer reaches here. When my slow pointer reaches here, my fast pointer reaches here. Now next my slow pointer is here, my fast pointer is here. The next my slow pointer is here and my fast pointer also reaches here. So now since my slow pointer and my fast pointer are at the same location, it means that there is a loop. However, one of the base scenario, one of the edge scenarios here can be, or let's not say edge scenario, one of the what do you call it? One of the negative scenarios here could be that it might not be a circular linked list at all. There could be, it could be like this. Correct. So in that case, we also have to make sure that we are keeping track that the next values are not known. Right. That is one of the base cases which we'll have to make sure. Now we have established that there is a loop. Now, how do we exactly find this start? Let's say this point. Let's mark it as red. Right? How do we find this point? Now, if you notice, so if we assume this length is L of my single linked list, right? And let's say the length of my circular linked list is C, all right? And the point where they meet is K, all right? All right. So what I can say is the distance, let's take it to the next chamber. So what I can say is that my distance traveled by the fast node is equals to L plus K plus number of loops plus length of my circular linked list. So the number of loops means how many loops am I taking here. So for this case, if you see, the number of loops is 1 for our fast pointer. Now the distance for the smaller loop would be, smaller pointer would be L plus K plus S C. S is the number of rotations, revolutions our smaller pointer does. Now I know that the distance traveled by my faster loop would be twice of the distance traveled by my smaller pointer. Why? Because this speed, right? It's twice as fast as my slower pointer. All right, so let's put that in the equation. What do we find? What do we get? We get L, so let's say 2L plus 2K plus 2SC is equals to L plus K plus FC. All right. Now let's simplify it. It will be L plus K is equals to F minus 2S C. This is a dot product. All right, so let's change it to something like this. C minus L. Now, what does this mean? What does this expression here means? So notice that this particular path would always be an integer, because we are saying the number of revolutions slower pointer makes and the number of revolutions the faster pointer makes, and those would always be integers. So this point is an integer, and doesn't matter how many revolutions they make, they would always reach this point, right? So what this thing means is, if I subtract L length from this point, I will get K. So at this point, if I subtract L, right? If I subtract L, what I should get this particular point. All right. So that is why the solution works. And that is why we say that we take our smaller pointer back to home, back to head, right? So what we do here is we keep our fast pointer here, right? And we keep our slow pointer here, right? And we keep moving it one step at a time. And at the third point, it will reach this beginning, and here at the fast pointer, also at the third step, it will reach here. Right? Because this -3 is K, and these are 3 steps which we are taking here. All right, I hope this makes sense. And this is what we call Floyd's algorithm. Here is the code for it. What we do is we take a slow pointer, we take a fast pointer, we check if there is a loop. Null pointers, very important. We check if my current node is null, and also I check if the next node of my current fast node is null as well, because for faster nodes we skip a node, right? So here we are skipping a node, and for slow we are taking one node at a time, not rushing it. So this notation is actually the equals notation, since what we are doing here is we are checking the value, and the value of our fast pointer is equal to the value of our slow pointer. If that is the case, then we have a loop, and then we break. We do not have to continue with our while loop here. And then if there is a loop, we take our slow pointer to the head, and then what we do is we again compare our values of slow pointer and fast pointer, and till they're equal. While they're not equal, we just keep moving them one node at a time, and we return the slow pointer. We can return the fast pointer here as well. So if it doesn't have if it do not have a loop in here, we just say no. Right? And let's say if you do not have a loop here, there would be some point where either this or this would be done, right? So it will come out, our has loop would still be false, and we will return null. So you know how to reverse the linked list? Well pun intended. And if you are not very much aware about this joke, I think you should spend some more time on YouTube. Searching for data structure questions. Okay, let's move forward. So reversing a linked list is basically again a bit tricky part, right? So the tricky part here is, again, I do a lot of blunder here, because I don't know how many nodes do I need to keep track of. And honestly, every time I solve it, I make a blunder, right? And I'm pretty much honest about it. So what happens when we try to reverse a linked list? So just saying, most of the time on lead code, if I could show you for this question, most of my answers are wrong, because sometimes I just return null, sometimes I return just the head and nothing else. And it happens with me a lot. And why? Let me show you. Let's say this is the linked list which we have to reverse, right? We take a head. We say that this is my current node. I need to have a previous node. Let's say the previous node currently points to null. All right. Now, what do I need to do is, in principle, my current node should point to my previous node, right? So the next node of my current node should be the previous node. So if I do that, if my previous node is null, so if I point my current node's next node to previous node, this thing goes away. Now, when we move ahead, so here, as you can see, we cannot move ahead because we have lost reference to this particular node and we cannot move ahead. And it happens a lot of times. So if we are doing it on a whiteboard or we are doing it on pen and paper, we can keep track of these things. So what I can say is, let's not do this yet. Let's keep it. Let's take a step back. Let's say we keep a reference to this node as well, right? Because we are losing this node. And if we do not keep a track, we would keep losing our nodes, even if we find a way to move forward. Well, we will not find a way to move forward for sure. So now what we do is, now I have a reference to this node, so I can lose reference to my node. Cool. My current node can lose its reference, and now it can point to null. Now, my previous node doesn't need to point to null anymore. My previous node can now point to my current node. And since now we are done with this node, what I can do is, now I can move my current node to the next node. It's pretty simple if you just do it in this way, right? And while we're doing it, just note down the steps, right? So what are the steps which we took? Number one, oops, I didn't report it. Ooh, it's huge. We took So what we did is we took our current node. Next thing, we took previous node. Third, we took the next node of current. Right? These are three things which we'll have to make sure that we have access to. Next thing is point current nodes next to ref. Right, this is what we did here. Point ref to current, cool, and move current. So now we have noted down our algorithm here. So now we know exactly what we have to do. And this is what we do here. We just keep track of our current node. We have a previous node. We loop it. We say, while my current node is not equal to null, I get the next node of my current node and mark it. And then what I do is, my next node of my current node is previous node. My previous node becomes, my current node becomes my previous node, and my next node becomes my current node. And I return the previous node, right? If we follow this structure, and I'm sure there would be less chances of missing out on the pointers and not being able to keep track of it. So that's it for linked list. Not exactly. So there are a lot of different kinds of linked lists, which we have skip lists, unrolled lists. Even in skip lists, we have 3 levels, 1 level, 2 level, and 3 level lists. What exactly are they? I'll cover them very from a bird's eye view, right? So let's talk about linked list of linked list, right? We call it unrolled linked lists. So we have blocks. And inside these blocks, we again have nodes. Right. So for solving this, we would certainly need a lot of object-oriented properties, because object inside an object, it's good to have object-oriented properties here. We point here. Let's point it back so that we have a track. All right. So we keep the track of head here at the block level, and we also keep track of head at node level. All right. It's n. It's an n. Right. Same here. We keep a track of this. We keep a track of this. Keep a track of this, and a track of this. Actually, we do not need to keep track of these because we already have a head. But inside these, we need to keep track of our internal heads. So why? Why do we need this at all? Right. So these kind of structures are really useful when you have to do faster searches. So let's say if your linked list is very, very search intensive, rather than reads or rather than writes like inserts or deletes, it is much more search intensive. Then using this kind of list helps a lot. How? Let's say you have to. Now let us understand the principle here. So if we want to have a list of size n, right? What we actually do is we try to have square root of n number of nodes inside every block. So here it is 3, so not 3, 9. So that's why we have 3 nodes inside every block. Now, if someone asks you find a node at point k, let's say the point is 6, I know where I can find it, right? So I know that we have 3 nodes here, then we have 3 nodes here and 3 nodes here. So 1, 2, 3 would be here, 4, 5, 6 would be here. I know that I'll have to go to this block, and it's just one step from this block. I do not have to go from 1, 2, 3, 4, 5. I do not need to do that. I just need to take one step, just one. And I know the head, 2, 3. That's it. I reach this point. Right. So it is much more efficient than single linked list and even double linked lists. However, the problem here is that insertions and deletions, since we will have to keep, we will have to maintain this property. This property is quintessential for unrolled linked lists. You have to maintain this property. So if I add something here, right, this block would move here. This block would move here, right? This block now will move outside. And what we will have to do is we'll have to create a new block. And point it the other way, actually. And this. Again, we have. All right. So this is what we would need to do for insertions. Now, what if I delete something? All right. So let's say let's say I deleted this list. So now I'll have to bring it back. This again has to come back. This would need to come back here, and this would not exist anymore. Right. So as you can see that how many operations we are doing here, we are essentially doing. So let's say we have n elements and we are dividing it among root and spaces. Then something like this number of operations may require. Right. So, but then and it is not very efficient, because for single linked list we saw that it is more or less a constant time if you know the unless we have to traverse to that particular element itself. But insertions and deletions at a position are constant time for linked lists. However, for array lists, it is not constant. It can be, it is of order n, even for arrays and array lists. So it is kind of in the middle. So our searches are faster now than linked lists, but our insertions and deletions take a hit. So we have to take a, it's a trade-off which we have to do between searches and insertions. All right, let's move to the next thing. The next thing is skip lists. So what are skip lists? So it is very similar to linked lists again, but yeah. Just longer boxes, nothing else. We have a value. Let's just, for the sake of simplicity, let's just say 1, 2, and 3, and 4. Right. And as I said, there can be 3 levels of skips which we can have. Right? They can be 2 levels as well, but just for this particular example, I am taking it all the way to 3. All right. So the first level is like our traditional linked lists. Right. Every node points to the other node, but here, if you see, it skips things. Let me just use some key color here so that it's so now this is a skip level linked list. All right. Why? I mean, we were happy with our single linked list, double linked list. We were still happy with our circular linked lists. So you can say that you told us about this fancy thing, which we don't know if we would ever use in our life, unruled linked list. Now we are talking about skip lists. Why would we anyway use it? So point is, these data structures are not usually used in everyday software development, but they are usually used for optimizing any system. When you have to optimize a system, you have to take your data structures, you have to push your data structures a bit further. You have to make them more performant. You have to morph them and make them like Ninja Mutant Turtles or something. All right. So what you have to do here is that why we are doing it is because if I want to find, say, a position, so let's say I want to find a third node of my linked list. What I could do is I could my head is at 1. From 1, what I could have done is I could have gone to 2. Then from 2 I could have gone to 3. 2 steps. Right. But let's say if I have this skip list, I can directly go from 1 to 3. cool, yeah, right? If I have to move to 4, I can directly move from 1 to 4. I do not have to do one, two, three steps, just one step. Now, consider you have a linked list which is of order of hundreds of thousands, or maybe even of millions. It might not be a nice idea to traverse every node at once, but what we can do is we can add some more abstraction to it, uh, one level or two levels, right? And make the reads faster. Now, one caveat here is that you might not want to do it if your linked list is write heavy, because managing these nodes can be a bit tricky. So make sure that we are not doing that. Right? The linked list is not write heavy. We are not doing inserts and deletes. All right. I hope this is still making sense. All right. Let's move to graphs now, right? And who doesn't like a directed acyclic graph? Right? We all like it. And for folks who have worked on big data and Spark, Apache Spark, know that directed acyclic graphs are at the core of Apache Spark. All right. So let's talk about how do we represent a graph. So a graph can be represented in 4 ways. The 4 ways which I know of, there can be more ways. First is adjacency matrix, adjacency list, a generic graph which say we want to make it entirely object oriented, and we want to put our other two representations on steroids and create something entirely different, encapsulated and whatnot. The next is adjacency set or disjoint sets. This is another way to represent graphs, and you would find these graphs and you would find these concepts in when you would have you know a bunch of graphs who have a cyclic nature, and then there is another bunch which has again a cycle. So you bunch them into a single graph and use disjoint sets there and use union on that. So this is out of syllabus for now, all right? Because I haven't prepared it. So we will just be talking about these three representations. Adjacency matrix. Adjacency matrix looks pretty easy, and believe me, it is easy. So what we actually do here is we get a list of vertices, and we just map those list of vertices to our rows and columns. And if there is a connection between between two vertices, what we do is we mark them as true, else they remain false. So here 1 represents a true and 0 represents a false. Okay, so like we can see that none of the vertices are pointing to themselves, so this particular diagonal would always be 0 because it is the identity matrix thing, where an identity matrix we have all the ones, so identity diagonal, let's call it. Now you know that A is connected to B, A is connected to C, yes, A is connected to, no, not connected to D. B is connected to A, yeah, for sure. B is not connected to B. B is connected to C, yeah. B is connected to D, yeah. So, and similarly, we just keep on filling up this matrix. All right. Now let's move forward. All right. Now this is the code for adjacency matrix. It's pretty simple. It's pretty easy. Now, if you notice, I'll show you in a second. Let's first talk about how we create an adjacency matrix graph. How can we create it? So we are using an array list here. Not array list, sorry. An array here. I always confuse array lists and array. Okay, so we use arrays here. And since we're using arrays, we have to define this bit size at the inception. When it's at the inception, means when we are initializing it. So while initializing, we have to provide a vertex count. And we create our adjacent matrix. That's it. That's all we do. Now we would need to add edges. So we would add edges, between our across our vertices. So here I would say is that we are taking vertex 1 and vertex 2, and whatever vertices are there, we just mark them as true. And for removal, we just mark them as false. And if we want to find out if there is an edge or not, we just check those vertices if there is an edge or not. Now, if you notice that there is this unusual method here is out of bounds. So what it usually do is, if you notice that this is now being used in all three methods, because I noticed that this particular condition has to be used in all these three methods, and this doesn't look really good to me. And repeating it in all three methods was looking a bit ugly. So why not move it out of these methods and use a common method and refer by it? So how does it work? I mean, why did we do it? Just because it's again a base case which we should always consider. And if our base case is being used by multiple methods in our problem in our data structure, we should make sure that we are taking it out and we are reusing that particular logic in all our methods. The reason is, if the logic is same in all the methods, and let's say down the line, if you change anything in your data structure, which results in changing this particular logic, you just have to change it at one place. You do not have to change it at places, right? So it is always a good practice, even while you are doing problem solving. Your bugs would be minimal. I know it might sound like a bit more code, but it's much easier when you get bugs, and which you get a lot, right? We do problem solving and we always get bugs. If you do problem solving without getting bugs, hats off to you. I can't do that. None of my programs run on the first time. So let's talk about this time and space complexity. So we know that the number of vertices here is V. So the time complexity here is of the order of V square, and the space complexity is also V square. Why is the time complexity V square? Because here, if you notice, we are initializing our matrix. And while initializing our matrix, it has to fill all the elements in that matrix, and that is essentially an n square operation. All right. Now, one thing I forgot to mention here is that my vertices here, which I'm taking, correspond to the indices, right? But then this data structure can change. I have just kept it. I've kept it like this just for the simplicity of graphs, because it could get a bit ugly if we start using objects here. You can certainly do that, but just for the sake of simplicity and comprehension, let's just assume that our vertices are the indices right now of our matrix. Now, when we should use these dense graphs? Well, we should always use this dense graph when the number of edges is proportional to the vertices, or we can say when our graphs are dense. What does that mean? What does that mean? So it means that if you notice that every node or every vertex here is connected to the other or other vertex, right? So if that happens, it's good to use an adjacency matrix. So other than that, let's say if you do not have these connections, then most of our matrix would be empty, and it doesn't make sense to use all that space just for a sparsely connected graph. So, but from sparsely connected graphs, what we have is we have an adjacency list. what is an adjacency list. Now, this is interesting. What we do here is we have a list, right? Or let's say we have an array of our vertices. And every element in our array is a linked list, right? So this is a linked list inside this. This is a linked list. This is a linked list. This is a linked list. All right. How do we actually represent it? Let's see. So we are keeping a track of all our vertices just to keep their indices, and we are keeping array of linked lists. Array of linked lists. This is how we read it. Array of linked lists. All right. So now we have to create our adjacent list graph. Again, we'll have to provide a vertex count. If we provide a vertex count, we initialize our vertices, we initialize our edges, right? We initialize our edges with the vertex count because it's an array. Now what we do is we add our indices, and in those indices we create our linked lists. All right. So now we know that where can we find our linked lists. Oops. So when we have to add an edge, what we do is from the vertices where we are indexing our nodes, indexing our array lists, we get the index, our source index, our target index, right? We create a source node and a target node. We have to make sure that while we are adding our edge, we are not adding it to a place which doesn't exist at all. So this is check here which we do. And then what we do is we set the value of our source and target, right? And at that particular index, what we do is we insert add head. Right? Say we had A, B, C, D. We had to add an edge from A to B. So let's say we had to add an edge from A to C. We added A to C. But then now we had to add an edge from A to B. So we add B at the head. At the beginning, basically. Now, it is very important to keep a track of the time and space complexities while we are solving graph questions. And it is very important to remind ourselves, and it's very important to to know that how these data structures and how these representations affect reads and writes and space. Right. So here's the table. I mostly refer this table. This table is basically from Karumanchi, and it is really good. And it's better to if we can keep a note of this table while we are solving questions and keep a mental map of it. It helps. Certainly, it helps. Now, let's put our graph representation on steroids and make it completely object-oriented. So, excuse me. Why would we want to do that? The main reason of wanting to create such a data structure is that your graph might not always be as simple as an adjacency list or adjacency matrix. So let's say that, let's take an example. We are creating a social network website, and you have just started writing some algorithm on your local. And what you do is you just, for the sake of simplicity and understanding, you just create an adjacency list. Let's say an adjacency matrix, because you realize you just have only a few members, maybe 100 members in your social network, and it's a closed-knit network. Everyone is connected to everyone, so let's just use adjacency matrix. It's just easy to maintain. Very good. Yeah, go ahead. Why not? So you do that, you create a matrix of Boolean type, and you add connections. However, now what you'll have to do is you'll have to make sure that the persons in that social network are just indices on that matrix. So you'll have to provide some hash code which will map those people to those indices in that matrix. Now, going forward, what you noticed was that okay, every person is connected to every person. Now my thing is going good. I have around 1,000 members on my social networking platform, and you know what? Not everyone is connected to everyone now, and it's not very closely knit. I have people from other networks as well, and there's no connection between the two networks, which I have. So why not just use an adjacency list? So you change your code, you change your logic, you use an adjacency list. But again, what you'll have to do is the way we were keeping track of our indices, you'll have to make sure that you can hash your indices, you can hash your people against your indices. Now, let's say from thousands you move to 10,000s and lakhs, right? And let's just assume we are still able to keep all that data in memory. Right? So if you're still able to keep the data in memory, it might not be very optimal or useful to have it in adjacency list way, right? It may now make sense to make things more abstract. So when we are making things more abstract, what we do is we use edges, we use vertices, and we use graph objects. Now let's start with an edge. Every edge will have two vertices, vertex 1 and vertex 2. We'll say whether it is directed or not. We will say whether it has any weight or not, and we will create constructors based on that. All right. So if you want to just put two vertices, just two vertices, with whether it's directed or not with weight, for sure. Vertices with just direction, whether it is directed or not, sure. And then certain methods for adding, deleting edges. Now, what if we have to do it for vertices? What if we have to do it for vertices? Right now, every vertex should have a specific ID. Now, why do we need to have a specific ID so that a vertex can be identified? Usually, it is a hash code of the data which we are saving. And it also helps us to index our data in case we need to. So that we can just, rather than traversing through the entire graph, we can just go to that point and use that data and get information about that data, right? Now, every vertex will have a list of edges because there would be edges going out, coming in, right? And based on the direction, we can identify whether the edges are going out or they're coming in, right? We can have the weight as well against these edges, and every vertex would have certain adjacent vertices, right? A list of adjacent vertices. So we would basically initialize a vertex with an ID because by initializing a vertex, we might not know what data we're going to put there, what are the edges, or what are the adjacent vertices which we'll have to add. So get ID, set data, get data. This is the part which is interesting. We add adjacent vertex. So in the current vertex, what we do is we provide an edge and we provide a vertex and we add that, right? And really, it becomes really easy because we just add our edge to the list and we add our vertex to the list, right? Now coming to graph. Now, what does graph? What does a graph have, right? So a graph will have a list of edges, and a graph will have a list of vertices, right? Because any graph, this let's move here. Any graph you notice will always have a list of vertices, and will always have a list of edges, and we'll know whether it is directed or not. Now, we initialize this graph, we initialize it, and then just adding methods. I'm not going deep inside it because it's just boilerplate, and most of the code is present in the GitHub link. So you can go ahead and find it out, check out the code, and write tests for it. If you are into Java and JUnit, why not write tests for it? I would very much encourage you to go and write tests and see if any of these data structures break at any point, or let's say if any of the code which I have provided you has bugs. Most probably it has, because I haven't got a chance to test it thoroughly. Yeah, I am a bit lazy. So let's talk about traversals. Now, the traversals which we use a lot are breadth first search and depth first search. Let it be graphs or let it be trees, we use these a lot. Right now, the problem which we face here is it's fine till the time we are doing recursions. Right, we can do recursions pretty well. We all know that, but a lot of times in the interview, what happens is they give us a constraint, and they give us a constraint that would cause a stack overflow exception if we just keep on doing recursions. So we have all learned that we use queues or stacks for BFS and DFS. But point is, I always tend to forget which one to use for what. So there is a neat trick which I keep in mind. That trick is BQ. Right? BQ is BigQuery. BigQuery is basically a database which is used for storing a large amount of data, used for big data technologies and data analytics. So BQ, right? Now BQ stands for BigQuery. It also stands for BFS with queues. Right? So that's one of the quirky things which I do just for remembering what to use. So if I have already used queues for BFS, then what do I do with BFS? The thing which is left, that's stack. Now, it might not be a good idea to remember exactly like this, because we will have to make sure that we know what we are doing, right, and why we are doing it. So let's see why we are doing it, why we are using BFS, and when do we use BFS, right? And do we know that we are using BFS? I'm not sure, right? At most, initially when we actually start coding, we are not sure, right? So finding all connected components. So connected components, like I mentioned at the very beginning of graphs, it is used for it is used with disjoint sets. Okay, and finding all nodes within one connected component, again, it is again a BFS, because you would just go inside that particular connected loop. Now, let's just see. I mean, these are a bit complicated examples, and I have picked these examples from Karumanchi. I'm a huge fan of Karumanchi, to be honest. Now, let's just see. When do we want to use BFS, or let's say if we want to use DFS, what is the concept behind it? Right. Let us try to understand how it works, how it actually just works. Now, let us consider a black pen. So let's say we have a graph. Let's just make it like a tree, an array tree, which is again a graph without any cycles. All right. Let us add levels to them, so it's easier for visualization. This thing can be blue. This thing can be green, and This thing can be yellow. Okay. Wow, this is horrible. All right. So what we do in BFS is we pick a node, we move down, we get all of its vertices or children, whatever you want to call it. We save it, and then we pick one children at a time. Okay. Now, what should we use? Stack or queue? I mean, we know that from BQ it is queue. Let's say you do not remember BQ as well. So let me just name them something. 1, 2, 3, 4, 5, 6. Okay, so now we have named our nodes, so it's good. We push n to our, I don't know whether it's a stack or a queue. I will create a logic, and then I'll try to find out whether I have to use a stack or a queue. Okay, so now I take it out and I print it. That's good. I have printed it. Now what I do is I try to get its children. So now it's not there anymore. Its children are 2, 3, and 4. 2, 3, and 4. Interesting. So now, if I use a stack, what would happen is I would pick it from here, right? And then I will have to get its children. We do not have it. Let's say what if we have, right? Let's say what if we have. Now we get its children. We add them, right? So we take 4, then we add some x and y right here, and then we print x and y. Doesn't sound to be a breadth thing, right? So I think stacks would not work. All right, we did not memorize anything. We just tried to do a dry run, and we realized that it is certainly not a stack, and it is most certainly a queue. All right, so now I take out 2, and I have 5 and 6. I add it to my queue. Since queue 2 is no more, I remove it. Now the next is 3. I get its children. I don't have any. I remove 3, then 4, then 5, and then 6. Cool. That's good, right? So if you notice that we did not have to memorize whether we should be using a stack or a queue. Right? We just tested our method. We just tested our algorithm, and we found out that it is most certainly a queue. It is not a stack. The same fundamental can be implemented with DFS as well. So if I use the same example, in DFS I should reach the last point, and I have to make sure that I reach the last point first, rather than reaching the breadth of it. All right, so what do we use there? Do we use a stack or a queue? Well, I don't know yet. So we have a stack, we have a queue. We put 1 here. I have to move deep in this. So I take it out, I print my 1. The next thing which I want to print here is 2. All right, so I take my children, it's 2, then it's 3, it's 4. Okay, now 1 is not anymore in here. I go to 4. Does 4 have any children? No, I print 4. Does 3 have an I remove 4. Then I go to 3. Does 3 have any children? No, I print 3 here. Then I go to 2. Does 2 have children? I say yes. So I add those children here, 5 and 6. And then I say that, okay, take out 6 and then we take out 5. Right? So as you have noticed that we have basically gone deep whenever we could. Right? Like for 1 we went till 4 and then we went till 3. And when we reached 2, we went to 5 and 6. Right? So here we just from the very initial part we notice that it is most certainly a stack. It is not a queue. Right? So now let's look at the implementation of it. Now, one of the things which we'll have to make sure that we keep a track of is vertices, right? All the vertices which we have already used. We have to make sure that we are not coming back to the same vertices again and again, because then it would be a cyclic, right? So we just pick the first vertex, we just mark it. It's that vast, it's huge, right? Because we have directed graphs, we have undirected graphs, we have cyclic graphs, we have acyclic graphs, we have directed acyclic graphs, we have a forest, we have a spanning tree, we have I don't know what we have connected graphs, we have I don't know what all what all we have. We have bipartite graphs as well, right? I mean the graphs which just the collections. We have 2 collections and they just keep referencing to one another. So we have all these kind of graphs which we have order of the characters in that language, right? Like in English, it is A, B, C, D, E, right? E, F, G, H, I, J, K, L, M, N, O, P. In here, W comes before E comes before R comes before T, and T comes before. So, and again, these are sorted, or we can say alphabetically or lexicographically arranged. Now, what does that mean? Now, let's talk a bit about this. What does it mean? We have words W, R, T. We have W, R, F, W, R, F. Then we have E, R, E, R. Then we have E, T, F, E, T, F. Then we have R, F, T, T. R, F, F, T. So what does it actually mean? So if I compare these two words, I can say that since it is alphabetically arranged, obviously W and R would come together, like in a dictionary, but T is coming before F. So T is coming before F. Interesting. Now, I'm pretty sure that W is coming before E. Yes, W is coming before E. All right. Now, what? W is coming before E. Other than that, F we cannot check anything else in this particular case. Let's talk about these two. So E is E, R is coming before T. Okay. So R is coming before T. And E is coming before R. So let's do one thing. Let's bring R here, and R is coming before T, and T is coming before R. T is coming before F. That is already established. Interesting. Now, what we can see is that W obviously comes first, and then it's E, then it's R, then it's T, then it's F. So the obvious sort here is W, E, R, T, F, right? It's that easy. Now, not exactly. So it might not be in this way every time, right? Not all your characters might just be such linear expressions of graphs, right? And just like a linked list. It might not be. So it could be something like, say, this. W connects with R, then R connects to F, right? So what we do is we keep a degree, right? So what is the degree in a graph? The degree in a graph is the number of incoming edges. So an incoming edge for W is, let's say, just for the sake of simplicity, let's say it points to T as well. We get such an example where we can make sure that W is before T. Right. So the degree of T is 1 and 2. All right. The degree of R is 1 and 2. The degree of E is 1. So what we do here is we first remove W. We first print it here. And we remove it. So 1 degree is reduced from T, R, and E. So now E is 0, R is 1, and T is also 1. Okay. Now we take the next zeroth degree character, which is E. All right. So we take it out of our graph. Right. So since we have taken it out, let me just put it like this. This is R. This is T. Right now, R is 0 because nothing is pointing to R. There are no incoming graphs to R, and T remains 1. Right now, we pick the next zeroth character, zeroth degree character, which is R. Now we print R here. Right. Now the degree of T is 0. Sorry, the degree of F was 2 here, now it's 1. Since the R is no more connected to it. Now we print T, and then we print F. Because after removing T, F would be the 0th degree character. And then at last we remove F as well. So our graph is now empty. And if you notice, following that particular, even making it more dense, we are able to get the same output. So how are we able to get this output? If you notice, we used an algorithm called topological sort. In topological sort, we essentially do the same thing, right? If you remember it from your n-ary trees or binary trees, you may call it a level order, right? Or a level order is also a topological sort. And for graphs, what we do is we find the least number of inbound edges, and we say that it is the degree of that edge, right? So let's start. So when we would be creating our order, what we would do is we would need to have a degree which will keep a track of degrees of every character, right? Like here, what we did here was, if you notice, right, we were keeping track of our degrees. Right, I'm going back. You can notice that we have been keeping track of our degrees. Let's not go that back. All right, we're keeping track of our degrees. So let's have a character map. Let's have a C map. Right, and we will have our characters and their degrees. Right, we'll take the same example which we used here, and we'll walk through the code one by one, right? And I will try to explain you this as we go through the code. So the next thing is take a graph. Now, what we have taken a graph is, if you notice that graph, it seems a bit different, and we haven't covered it. It seems it is a map. Why isn't it a list or an array? And in a map, we have a set y. So if you consider this, it is basically an adjacent list, an adjacency list, right? Because in adjacency list, we have an array, which is basically a map. And then inside a map, we have a set, which is a linked list. So rather than using a linked list, we are using a set y. I will come to that as well, because we would need to reference those vertices a lot, right? And rather than using linked list, using set and a hash set makes a lot of sense. So first of all, what we do is we build our graph, right? The first step, which we did here as well, was we built our graph by checking these things. Now, what did we do while building that graph? So if you notice, first of all, what I did was I made a note of all the characters, right? All the characters. I made a note of all the characters, and so let's make a note of all the characters. And create a character map as well, just initialize it. So we have WERTF. We have W, we have R, we have T, we have F, and we have E. And the degrees are 0, because we don't know what their degrees will be, so we just initialize them to 0, right? All of them. Right? Now we have another hash set of characters where we store our characters. The sequence doesn't matter, because in unordered sets or hash sets, there is no sequence at all. We do not keep a track of the sequences. Cool. Now we have our character set. What we do here is, rather than we create a copy of our character set, so that we do not. So it's basically a coding practice. Whatever input we are getting, we do not mutate it, but rather than we create a new set. And we create a graph. Now, how do we create a graph? Now, if you notice, what we did in the previous step, we were checking 2 words at a time. Right? We are checking 2 words at a time. We do the same thing in the code as well. We start with our word index, right? We take the length, just one less, because we need to take the next index as well. So just so we do not face any overflow issues, and we increment it. Now we get the current word and we get the next word. Now with the current word and next word, if you noticed, what I did was I checked, okay, W is equal to W, R is equal to R, but hey, T is not equal to F. So we can get some relation here. So iterating through all the characters, right? If my character at this particular index is not equal to my next word's character at that particular index, there's something interesting which I can do. And what is that interesting part? What I can do is, from the characters, I will remove that. I will remove that particular character. In this particular case, I will remove what? I'll remove T. Right? Why am I removing it? Well, we get to know it at the end while we are putting all the characters in the graph. So whatever isn't used, whatever isn't referenced, we just put all those characters in our graphs, and those characters do not have any vertices at all. Right? So let's move ahead. Now, what we are saying here is, if the graph does not contain any character yet, then add an empty set to it. All right. So what is our graph? We have created a graph. So a graph is, again, a character and a set. Right. So right now, I do not have any character. We have not initialized our graph at all. So what I'll do is, I know that the current character, which I'm referencing, is T, right? And what does it have? It has F inside it as its edge, as its adjacent vertex. That's all what we are doing here. So we initialize with an empty hash set, and then we add it, and then we compute our degree. So if you notice, we are keeping our degrees here. Vector map or degrees, right? We're keeping our degree here. Now the degree of F increases. See, F is the next character, and we are increasing its degree. So now F becomes 1. That's cool. Makes sense. Now we go ahead and we get to the next word. We get to these two words, and here we see that W and E are different. One more thing I just want to clarify here is that we're taking the minimum length of current word in the next words, because just so we do not overflow our indexes, right? We do not go out of bound of our indexes. So let's see. Yeah. So again, we move to the next word, and we go character by character, and W and E are different. So we remove W now from our character set. We have removed W from our character set, and we are sure that W has to be added to our graph, and the next character has to be added as its adjacent vertex. So we do W, and the adjacent vertex to my W is E. Right? Adjacent vertex to W is E. All right, and I increase the degree here. It's coming out pretty nice. Now we go, then we check the next character, R and R, they're equal, then we can't go further because it's just two characters, right? Now we check these two, ER and ETF. E are same, R and T. We go to R and T. Now for R and T, we remove R. We add R to our graph. The vertex to the graph is T, because R is pointing to T, and we increase the degree of T by 1. Cool. Now we go to the next set. This is the next one, ER. Obviously, we remove E from our set, right? And we put it here, and let's just say we put it here, and it's pointing to R, right? And we increase the degree of R by 1. That works. Now, let's come here. So TNF, same thing we do with TNF and the other. It's actually T. Else it would not make sense. It has to be T. All right. So T comes after F. So we have already covered that, I guess. Yeah. So now what we have here is that if you notice, we have W, right? Oops. Let's change our color, right? We have W as cardinality 0. All right, and whatever we have left is F. So I mean, just if you just go back to the code, F is left, and F is basically a leaf of our graph, the end of our graph, which doesn't have any more vertices pointing out of it in the outwards direction. So we just mark it null and we return the graph. Now we basically do a topological solve. How are we doing it? The first thing which we do here is we get our we get all the vertices which have 0 index, which have 0 degree, and we add them to our queue, right? And once we add them to our queue, what we do here is we take a string builder just to note down all our result, and then we pull from our 0 degree, from our queue, right? We get a vertex, we append that to our result. Now we get the set of neighbors, right? So if the neighbors is not null, let's say if there are no neighbors, we just remove that graph, right? Like we did while we're doing it, we're removing it, right? So the same thing we do, we remove our graph, right? And then inside our, if we find a list of neighbors, what we do is we count the degree. We reduce the count like we did here while we were doing it. We were reducing count of our neighbors as and when we were removing our 0 degree vertex, right? We are reducing count of all our neighbors, right? And if the count is 0, we are again adding it to our queue, which is a 0 degree queue, right? And if it's not 0, then what we do is we update its degree, like we did it here, right? We were updating its degrees, and if they were 0, we were just popping them out. In theory, we would be adding them to queue and popping them out, right? And at the end, once this entire process is done, what we do is we remove that vertex from the graph itself, right? So removal from sets is much easier. Okay, so that's the alien dictionary thing. Sorry. Now, let's move forward. And I hope you guys are tired as well. So that's it. I know it got a bit boring with graphs, but graphs, I hope I could make it a bit interesting for you. A final few tips for interview. You notice that while I was going through my examples, I was drawing stuff, I was explaining it, and I was talking to you. I mean, here I have to. I mean, but then make sure that while in an interview, you always talk to the interviewer, right? So I take mock interviews of professionals and students. I mean, not inside Google, but outside Google. Those who want to prepare or do have any interviews or want to get a feel of how these interviews feel like. And I almost a lot of times, I mean, if not every time, a lot of times I give this feedback to my candidates that speak out loud, right? Whatever you're thinking, just speak out loud. So it helps you. It helps the interviewer to understand what you're trying to do, right? Because this question, like, this is not a very typical question which you get and you can solve looking at it, right? It takes a bit of practice to understand what is exactly going on here. All right, it does take a bit of practice to actually understand that the behavior which we are seeing here is actually a topological sort, nothing else. And if we know the topological sort, then we can be sure that lacking or at which point you are being stuck. They can help you, right? Everyone needs help. They are looking for a person who can be their teammate in future, right? They're not looking for someone who can solve the questions by themselves. No one can. They would always find for someone who is collaborative, who talks. So always be in a conversation with your interviewer. Right? It's very, very important. Now, like I mentioned earlier, you should almost always try to get an approach first. If you think that the problem is difficult, right, discuss it with the interviewer and then go to code. Because if you're directly jumping onto code and if you're not clear about how to approach it, a lot of times what will happen is you would implement it wrong. However, if you're very confident about your code, right, if you know that you know the solution to it, you can code it down, it's very clear in your mind, it's still a good idea to write down the algorithm, at least. When I say the algorithm, the steps, right, as in terms of comments while you're writing your code. So that what it would help you to do is, it will help you to keep track of what you need to do next. What are the base cases which you have to take care of, right? So make sure that you do that. It would be it will be very, very helpful to you while you are doing an interview because you will have a structure. The next thing is, I get a lot of questions that I'm doing lead code. I've done 600 lead code questions. Is it enough? To be honest, it could be or it could not be. It totally depends upon how you're approaching those problems. If you understand the concepts, if you understand how to approach a problem, obviously, it's enough. Even 100 questions, 200 questions would be enough, I guess. However, if you're just cramming them up, or if you're not understanding the concepts behind it, it might not be, you might not be actually doing the correct thing. All right. So these are the few things which I wanted to bring out. And yes, always use correct variable names. Don't use ij and k. It just confuses you while you're coding. I have seen a lot of instances in real interviews and in mock interviews that people have lost track of their variables. Since they're using IJK, they do not know what to do next, and if they have created a variable or not, or if they have created their using that variable or not. It happens a lot of time. So make sure that you do not do that mistake, right? Give meaningful names, small names and meaningful names. If the lifespan of that, if the scope of that variable is very small, it's fine to name them ij and k. If the scope of the variable is not so small, I would say that give them some meaningful names. Let me give you an example of such thing. If you would have noticed my code, I never use ij and k. That is basically by nature to me. I never use ij and k at all. So let's see if we have used more. Right, so here, if you see that I'm using W index, right? Although scope of this is small, but still I'm using W index because it makes me understand that is the index of words. Right? I could have used I or J, but it doesn't give me any context about what it is. Here it gives me context that, okay, it is a word index. That's it. Please throw any questions at me. Another link is open. The video is open. I can read your chats if there are any. If you have any questions, I'm open to them. And if you have any doubts after this session, please feel free to ping me on LinkedIn. I have a GitHub account. Feel free to check out these put this code, add tests to them, find out bugs.
Thank you so much, sir, for enlightening us with this amazing session. We are grateful to you for sparing your time. Also, GDSA Banasthali Vidyapith's first open source project, Code Crossroad, is live on GitHub. Contribute to the project, submit the solutions, and have a chance to be featured as a contributor in this project. This project contains the carefully compiled data structures and algorithm questions asked by the companies that visit Banasthali Vidyapith on campus. The details for the same are mentioned in the description below. Stay tuned on our social media handles for more updates.